Okay, we can go ahead and get started. Good morning, everyone. Thank you. Sorry. Good morning, everyone. Thank you for joining us for the 2025 Nick Besley Award webinar, featuring a presentation by our 2025 award recipient, Professor Justin Talbot from Clemson University, who is joining us today to talk about some of his work. A quick introduction to Nick Besley himself. He got his bachelor's in chemical physics from the University of Sussex in 1994, and then went on to do his PhD in theoretical chemistry at the University of Birmingham in 1997. And then he did 2 postdocs, one with Professor Jonathan Hurst at the Scripps Institute in the US, and then one with Professor Peter Gill at the University of Nottingham in the UK. In 2022, he started his own independent scientific career at the University of Nottingham with an EPSRC Advanced Research Fellowship, and he was promoted to full professor in 2018. He and his group added a lot of really powerful new functionality to QChem over the period of 2 decades, and their contributions led to QChem becoming a leading package for the simulation of spectroscopy of core electrons. He also contributed to the development of new exchange correlation functionals, novel methods for computing electronic excited states, extensions of TDDFT for prediction of X-ray absorption spectra, and methods for calculating harmonic and anharmonic vibrational frequencies within a partial Hessian formalism. Nick was an inspirational teacher and supervisor. I never got to know him personally, but I have heard that he really cared a lot about mentorship and also about collaboration. He collaborated with both theorists and experimentalists and worked very hard to bridge the communication between those 2 groups. And obviously from a scientific standpoint, also the work that he's done has contributed phenomenally both to QChem and also to the scientific field and computational chemistry in general. In 2021, in June, he unfortunately passed away after a tragic cycling accident near his home in Nottingham, England, leaving behind his wife Elena and their daughter Emily. And the award, the Nick Besley Award, was established in his honor, to honor his memory, and also to recognize excellence in the development or application of new methods for computational spectroscopy in QChem. This award is given annually. It includes a certificate and a monetary prize, and it commemorates the contributions of Professor Nick Besley, who is remembered for his multifaceted contributions to electronic excited state theory and methodology. And just a couple of the previous award winners, Dib Height and Florian Matz and Kay Carter-Fenk, from the past 3 years. And then this year's award winner is Justin Talbot from the Clemson University. And a statement from the award committee, Justin is recognized for his contributions towards the computational vibrational spectroscopy of hydrated ions and the development of efficient methods for non-adiabatic dynamics simulations in QChem. So we have this award for you. Congratulations on receiving the award. You'll be receiving a physical version of this award in the mail, along with the monetary prize associated with it. So thank you to Professor Talbot. We're really excited to have him joining us this morning. A quick introduction to Professor Talbot. He is, he did his bachelor's in physics and applied mathematics at the University of Utah, where he also did his PhD work with Professor Ryan Steele, working on applications and methods of for vibrational structure theory. He then moved on to do a postdoc at UC Berkeley, where he worked collaboratively with Professor Martin Head Gordon, Dr. Stephen Cotton, and Professor Bill Miller to study electronic structure and non-adiabatic molecular dynamics, which has been ongoing work throughout the duration of your career, I think. He is now an assistant professor at Clemson University, where he leads a research group focused on ab initio electronic structure methods and molecular dynamics simulations with applications to solar energy and also some green energy applications. And he has also made significant contributions to QChem specifically, including the development of novel methods for computational vibrational spectroscopy and non-adiabatic dynamics. So we're really excited to have you here to talk about some of the work that you've been doing and some of your research. And congratulations on receiving this award. And without any further ado, I will go ahead and hand things over to Justin. So.
Great. Thanks so much, Shannon, for the introduction, and thanks to the award committee for the award. And I'm really excited to talk to the QChem development community today about some of the work that I've done as both a graduate student. I'll touch on that a little bit, but mostly the work that I've done with Martin and Bill at Berkeley as a postdoc. And, when I was starting out, when I first learned about theoretical chemistry as an undergrad, when I started doing research, it was I had met Ryan Steele, and when I'd met Ryan Steele and we decided to work together for undergraduate research, QChem was kind enough to give me a 10-year user license at that time. And I think that was QChem 3. That was back in 2012. And so QChem, took a gamble on me when I was starting out as a scientist, and so I have a bit of a soft spot for QChem. So I'm very excited to talk to you guys today about my work. Um, Over the years, I've used QChem to do lots of different types of calculations and simulations. I've focused some on photoinduced relaxation. In particular, I focused on things like intramolecular vibrational redistribution, vibrational energy transfer. Um, also looked at things like intersystem crossing and kinetics and things like photoinduced relaxation. Um, I've done some work developing methods for binding thermodynamics and energy decomposition analysis. We've looked at things like adsorbate binding on metal organic frameworks. And at Berkeley, we developed a free energy decomposition analysis that uses ALMO EDA. As a graduate student, sorry. As a graduate student, though, my focus was in vibrational structure theory, and in particular, we were using vibrational structure theory to make predictions about vibrational spectroscopy. And we were looking at these water oxidation catalysis systems, where you have some big water oxidation catalyst here with a transition metal center that binds a hydrogen-bound water network. That hydrogen-bound water network can exhibit infrared signatures, infrared spectroscopic signatures, um, that are really quite anomalous and quite strange. You get things like in this ruthenium water oxidation catalyst, you can get these really broadband spectroscopic signatures that cover 600 or so wave numbers, and really identifying the sort of vibrational structure, identifying the quantum transition that underlie these really broadband peaks, or something that's of really great interest to experimentalists and to theorists too. And so I did a bit of work looking at hydrated ions to try to identify some of these signatures. We've looked at things like the water iodide anion. We've looked at hydrated cesium. And we also looked at the water dimer cation. And the water dimer cation was a really interesting study that we did, although it's been about 9 years now. When you ionize the water dimer, you get a hydronium hydroxyl radical pair. And this hydronium hydroxyl radical pair forms H3O plus and OH minus, or OH dot. And if you were to measure the infrared spectrum of this small water dimer, what you find is that, near the bending region, about 500 wave numbers above the water bending region, you get these progressions of peaks. And this happens in a lot of hydrated ions, but in the water dimer cation, what you get is you get this triplet feature that occurs near 2000 wave numbers. And the source of this triplet feature, the underlying vibrational transitions that make up this, are something that weren't really well known at the time. And this system is really interesting because when you ionize the water dimer, there's a competition between forming the hydronium hydroxyl radical or forming the water-water cation. And the vibrational degree of freedom that connects this water-water cation with this hydronium hydroxyl charge transfer state is a hydrogen bond or a shared proton stretching motion. And that shared proton stretching motion undergoes a really large amplitude transfer. There's really a large amplitude proton transfer that happens, which sort of interconverts between this water-water cation and a hydronium hydroxyl state or structure. And what we found is that the coupling of this large amplitude proton transfer is responsible for these types of peaks through what's called resonance interaction. And really what we found is that by sort of simulating the vibrational structure of this thing, which I'll talk about in a minute, is that vibrational motions that make and break the hydrogen bond are responsible for these types of resonance interactions. And, we use these really big sort of brute force Hamiltonian diagonalization sort of method where in multiple dimensions, where if you use something like 6 vibrational modes of this thing, you can recreate this triplet feature in that region. And if you compare that with the experiment, so this is the experiment that I was showing before, we find that, we're within 50 or 100 wave numbers using this eigensolver-based approach. And from this eigensolver-based approach, we can really identify what the different vibrational motions are. We find that if you have this shared proton stretching motion here that comes in at 1950, that there are combination bands off of this bending motion. These combination bands off of this bending motion gain oscillator strength. They share oscillator strength with this shared proton stretching motion and lead to bright signatures. And we find that, a rotation of the hydronium coupled with the bending mode of the hydronium falls right near this shared proton stretching motion, which leads to a resonance interaction. And we find that this bending motion combined with an oxygen-oxygen stretch, so removing the proton acceptor, leads to the other resonance interaction. And to do these types of calculations in QChem is really not trivial because what we're doing is we're solving this Schrodinger equation, and we're solving the Schrodinger equation in 6 dimensions. And so there's sort of some searching of vibrational degrees of freedom that sort of can give you the right interactions in that region to lead to the resonance. And what we found back then was that if you take 5 normal modes of this water dimer cation, if you take the oxygen-oxygen stretching motion, removing the proton acceptor by pulling apart the hydronium and the hydroxyl, and if you take this A double prime bending mode, you take the A prime band here, and you take the shared proton stretch, and you need this exterior stretch too, this flanking OH stretches. If you take those 5 normal modes and you combine them with a rigid rotation of the hydronium, so this is a pure rigid rotation of the hydronium. If you take those 6 vibrational degrees of freedom, take the Schrodinger equation, calculate this 6-dimensional potential energy surface using something like MP2. We used RIMP2 with a CC-PVTZ basis set. We calculated 184,000 configurations at the time, 184,000 RIMP2 CC-PVTZ calculations of the potential and the X, Y, and Z component of the dipole moment hypersurface. You take those, you put them into this big Hamiltonian and diagonalize it, and what you get is you get these results here, which matched quite well with experiment. So we were very happy with the results of that. But these were very involved these were very involved calculations. And, you know, yeah, we used 184,000 quantum chemistry calculations for the water dimer cation, but there were certain cases where that number would go up into the 500,000 or 600,000 QChem calculations. So these are really big sort of QChem calculations on really small systems in order to really identify these spectroscopic signatures. But really so that was what work that I did as a graduate student, but really what I want to talk to you about today is I'm going to talk to you mostly about a paper that we did in the Nick Besley Memorial issue of Molecular Physics that involved an ab initio approach for non-adiabatic molecular dynamics. And I'm going to talk about I'm going to show a test case where we can actually use QChem doing excited state dynamics to predict things like ring opening in these small 5-membered rings. And non-adiabatic dynamics is important in a lot of technical applications. One is solar energy catalysis. So here I'm showing this is a ruthenium bipyridine complex. This ruthenium bipyridine, or sort of analogs of this ruthenium bipyridine complex, can be employed as dye-sensitized solar cells. And what this means is that you can form thin film semiconductors with these dye molecules, and you coat a traditionally non-semiconducting material, something like TiO2. Light comes in and excites an electron in this dye molecule. That electron then goes through a series of non-radiative relaxations. That series of non-radiative relaxations, the states that they go into are either good or not so good at injecting the electron into the TiO2 band gap. There's also some application in like biological systems. So here I'm showing light harvesting complex 2. This is a bacteria that form these rings of these different bacteria chlorophyll molecules, like B800 or B850. And these rings of bacteria chlorophyll molecules can transfer energy between them on timescales of like a B800 to B800 energy transfer is on the order of half a picosecond. An 800 to 850 transfer happens on about a picosecond, or a B850 to B850 bacteria chlorophyll molecule happens much faster, on the 50 to 150 femtoseconds. It's also important in atmospheric chemistry where, you know, automobiles, combustion, vegetation create pollutants into the atmosphere. Those pollutants interact with photochemical oxidants like NO2 or O3 or other small particulate matter to form these volatile organic compounds. When these volatile organic compounds interact with light, they undergo these large amplitude geometric distortions. These large amplitude geometric distortions are driven by big changes in the electronic state. It happens through this non-radiative or non-adiabatic relaxation to form these different conformers, or even sometimes can form radicals, can break bonds and form radicals. The way in which we usually think about this type of non-adiabatic relaxation are with these simple reaction coordinate diagrams. So here I'm showing a typical reaction coordinate diagram that you would see in like general chemistry, where you have a reactant well and you have a product well and there's some barrier. If the energy of the particle is less than the energy of the barrier, then it'll just sort of oscillate around in the reactant part of the potential. But if you were to excite this with light, like say you make an S0 to an S1 excitation, well, the excited particle now on S1 has sufficient momentum as it heads towards the minimum. And if this picture were correct, then the particle would just sort of move around at the bottom of this S1 well. But we know when these potential energy surfaces get close to each other that there's what's called a breakdown of the Born-Oppenheimer approximation. And this breakdown of the Born-Oppenheimer approximation means that you can have transitions between different electronic states, or you can have rapidly changing electronic character. And these transitions between states could drive the system. The system could undergo or the particle could undergo a non-radiative relaxation and go from S1 down to S0 and either end up in the product well or end up back into the reactant well. And really the driving question of this type of research, understanding these types of non-radiative transitions are, what are the electronic and nuclear rearrangements that drive this type of electron-nuclear coupling? So this is a coupling between the electronic and the nuclear degrees of freedom. And the way in which we approach this is with a sort of mixed dynamics approach. For the electronic rearrangements, we use density functional theory. In particular, we use TDDFT, and I'll talk a little bit about that in a minute, but this gives you, as you guys know, this gives you really specific information about the electronic rearrangements and about the electronic structure. And then for the dynamics, we propagate trajectories using classical molecular dynamics. So we're propagating using classical molecular dynamics on these TDDFT surfaces. And so sort of the background behind this is that if you start with the molecular Hamiltonian, so here I have just the molecular Hamiltonian, where you have the kinetic energy of the nuclei, the kinetic energy of the electrons, and then you have the potential terms, the nuclear, nuclear, electron, nuclear, and electron, electron. This gives you something that looks like a potential energy term U, a kinetic energy term of the electrons TE, and then the nuclear kinetic energy. And if you make the Born-Oppenheimer approximation, the Born-Oppenheimer approximation assumes that there's a timescale separability between the nuclear degrees of freedom, big R, and the electronic degrees of freedom, little r. And if there's this timescale separability between these two degrees of freedom, the nuclear and the electronic degrees of freedom, then you can approximate this molecular Hamiltonian into two Hamiltonians. One Hamiltonian that involves the electronic part, this is what we solve with QChem, of course, and another Hamiltonian that involves the nuclei. And each of these Hamiltonians have their own corresponding Schrodinger equations. So you have the electronic Schrodinger equation, at which the eigenvalues of this Schrodinger equation as a function of nuclear coordinate give the potential energy surface. And you, of course, have the nuclear Schrodinger equation, which is what I was solving in the previous slides. So to propagate the electronic degrees of freedom, we propagate on the electronic Schrodinger equation. So here I'm showing the electronic Schrodinger equation that's been integrated. So here you have ck dot, which is the time derivative of the electronic coefficient ck. You have this time-dependent overlap term between electronic state k and electronic state j, and that equals the coefficient for state k times the potential. The first approximation that we make in these classical molecular dynamics is to assume that the nuclear motion can be described by a single trajectory r of t. This is not quantum mechanics. We're assuming that the particle has a definite position r of t. And when you make that approximation, the time-dependent Schrodinger equation now looks like this, where you have this term that now is the derivative coupling term, dkj. That's called the derivative coupling, which we calculate with QChem. And then you have the time derivative of the, you have the time derivative of the position r. And then they're multiplied, of course, by their electronic coefficient ck and the derivative of the electronic coefficient. Now, in Meyer-Miller dynamics, we make an additional sort of we place an additional constraint on solving this time-dependent Schrodinger equation. And that additional constraint that we make is that the electronic coefficient ck must evolve according to Hamilton's equations. And if these coefficients ck must evolve in time according to Hamilton's equations, then they can be written as a canonically conjugate pair of electronic positions and momenta. So here, this is like a momentum for state k, and this is a position for state k. And we can write, if we're going to require that these electronic coefficients evolve according to Hamilton's equations, we can write the C's, the coefficients for the electronic states, in this way. And you can play around with this a bit. There's a bit of algebra involved, but you can play around with using ck in this form and plugging it into the time-dependent Schrodinger equation. And if you sort of play around with the math a little bit, what you arrive at is that is this for a Hamiltonian. So here we now have a Hamiltonian that involves four variables. We have a Hamiltonian that involves, the position and momentum of the electronic states. And we have the nuclear position R and the nuclear momentum P. And in the adiabatic representation, the Hamiltonian looks like this. We have the potential energy term, which has a coefficient which looks a whole lot like a harmonic oscillator. I'll get to this gamma parameter in a minute, but it looks like a harmonic oscillator. And then for the momentum term or the kinetic energy term, we have this derivative coupling between states J and K, and it's multiplied by the position of state J and the momentum of state K. Now, one correction you could make to this, so if you were to assume that there was no gamma here, that gamma was zero, then this is Ehrenfest dynamics. This is exactly Ehrenfest dynamics. But an additional sort of approximation that we make is that we place 0-point energy into the electronic states. And this 0-point energy comes in with this gamma parameter. So if gamma was a half, that would be the quantum harmonic oscillator result. We find gamma of about 0.3 to be pretty good, or we have even techniques in QChem when you run these dynamics that can select gamma based off of the given trajectories. Well, with these four variables, we propagate the dynamics classically using Hamilton's equation. So we propagate the electronic position of state I using, and the momentum using Hamilton's equations, and we propagate the nuclear degrees of freedom, the nuclear positions and nuclear momentum, also using Hamilton's equation. So we're solving this coupled set of differential equations at each time step. And now this gives you nothing about quantization. You could calculate this n value at each point along your dynamics, but there's nothing that actually quantizes this to a specific electronic state. And so Steve Cotton has worked really, and Bill have worked, put a great deal of work into developing a quantization procedure. And that quantization procedure is called the symmetric quasi-classical approach. And the symmetric quasi-classical approach takes these n values, these occupation values for each potential surface, and bins them according to windowing functions. So here, if you have state 1 and you have state 2, and the occupations are sort of moving between the two, anytime that one of them falls within one of these windowing functions, we say that it's assigned to that given state. So if it's in n1, we say that it's assigned to state 1. If the value of n here falls within n2, we assign the triangle around n2, we assign it to n2. For the electronic part, we use TDDFT, and we use TDDFT in the Tamm-Dankoff approximation because the Tamm-Dankoff approximation gives you a wave function-like approximation to the electronic excited state. So with Tamm-Dankoff TDDFT, you're really solving an eigenvalue equation. This eigenvalue equation involves the A operator with the T amplitudes and then the excitation energy omega. And this is, again, a wave function like approximation to the TDDFT states. For the derivative coupling, we use the Hellman-Feynman theorem. So here we have the derivative coupling, which we use the Hellman-Feynman theorem to get this expression. And people like Joe Subotnick and John Herbert have really shown that this expression here really is exactly the same as the expression you would get for an analytic gradient in TDDFT with a different left and right T amplitudes. So if here capital I, state capital I and capital J are the same, then you have the gradient. You have the nuclear gradient for that excited state. Well, with that expression, you can form a generalized expression for the analytic derivative coupling, and it involves a few terms. So one term involves a contraction with the derivatives of the core Hamiltonian, contracted with the relaxed difference density matrix. And in these Meyer-Miller and Ehrenfest dynamics, we have to calculate this for all of the states at each time step. So if you have F electronic states, you have to calculate this term for F times F plus 1 over 2 states at each time step. We have the 2-electron component where you have the 2-electron integral derivatives contracted with the separable 2-particle density matrix. You have F times F plus 1 over 2 of those. You have the energy weighted density matrix, which is contracted with the overlap integral derivatives. And then for TDDFT in particular, you have two terms. You have the one electron part, which is the exchange correlation Fock matrix derivatives, which get contracted with this difference density matrix. And you have the exchange correlation integrals. These exchange correlation integrals get contracted with what are called the transition density matrices. So at each time step, you have to calculate this for all of the states. So it's quite a big calculation at each time step. And so one thing that we did is we took the code that was already there in QChem, which that code could calculate this derivative coupling for a given pair of states, and completely reworked it so that we parallelize the contractions over multiple density matrices. And let me show you what I mean by that. So if you have, let's say you want to calculate a gradient here, A, and you want to calculate a gradient for state 1, well, you would calculate the corresponding density matrix, and then you would calculate the integral derivatives, B of R, and then you would do the contraction. And you would have to do that for each pair of states. Well, these integral derivatives don't change when you do the contraction. So you're basically calculating these integral derivatives multiple times, which is unnecessary. So the new routines that we use in the code are that we basically swap the order. You calculate the integral derivatives up front, and then with a given set of integral derivatives, you do a contraction over all f times f plus 1 over 2 states. And that gives you all of them basically at once. And this speeds up the calculation actually pretty substantially. So for the electron-electron part, for the 2-electron integral contraction part, we find that, for something like 600 basis functions, for an alkane chain, you get a speed up of something like a factor of 3 if you calculate the integral derivatives first and then do the contraction. For the exchange correlation part, you get about a factor of 5 speed up. And for the couple perturbed SCF solutions, which you need in order to calculate the relaxed density matrices, you get about a factor of 3 speed up. So we got this pretty substantial speed up, which allows us to do these dynamics over multiple states, basically. Okay, so we've used this to in the paper, in the Nick Besley Memorial paper. We use these dynamics to make some predictions about bond breaking of a 5-membered ring. And the ring that we chose was selenophene. It's selenium in this 5-membered ring. And in the ground state, selenophene has C2 symmetry, C2V symmetry with a C2 axis going right here. And the highest occupied Kohn-Sham orbital has like a bonding interaction basically between the carbons on the sort of flanking carbons. And then it has a lone pair p electron on the selenium. Well, if you excite selenophene with light, the bright excitation is a pi to pi star excitation. So you take this pi orbital and you excite it into a pi star where you now get some sort of anti-bonding interaction off of these carbons here, but you still have this p type electron on the selenium. Well, nearby is a pi sigma star state, and this pi sigma star state can result in 2 different configurations. One is where you cleave the selenium carbon bond and form a radical, or you can form a radical basically on either side, so you get a double well potential. Now, in the pi star state, in this red pi star state, the excitation, this anti-bonding interaction of these flanking carbons, drive the system to really break planarity. It really wants to move in and out of plane a lot more, and it's energetically favorable for it to break its planar structure. Well, the difference between the pi star orbital, where you sort of where you've puckered the ring, and this sigma star orbital, where you form this anti-bonding interaction between the selenium and the carbon, is a rotation of the p electron on the selenium. We can predict the population transfer between the states. So here, if you start in a pi star state, we predict basically with our Meyer-Miller dynamics or SQC dynamics that the population transfer happens very fast. It happens within 10 femtoseconds from pi star into pi sigma star, with some slight population going into some higher level states. And as I was saying, the difference is that this pi star orb, the difference between this pi star orbital and this sigma star orbital is that there's a rotation of this lone pair p electron on the selenium. So as the ring puckers from the pi star excitation, the lone pair on the selenium wants to rotate. Well, that rotation forms the anti-bonding interaction, which destabilizes the ring. So I have a trajectory here that shows that rotation from one of the trajectories from the SQC calculations. And you can see, so I'm going to play this, as you can see very quickly, you form the anti-bonding interaction and then break the ring. So here you've rotated the p electron on the selenium. That rotation of the p electron forms the anti-bonding interaction, which breaks the ring and forms the radical. We can predict structurally how long it takes to, break the ring. If you use a predictor that's a maximum minus minimum selenium carbon bond length, then on the ground state, you have the same selenium carbon bond lengths on each side. On the S2 state, the S2 minimum, the same thing happens where you've broken planarity of the ring, but you still have the same bond length. But once you've broken it, you have a difference of 0.776 angstroms. So on the y-axis here, I'm showing the time in femtoseconds. And on the x-axis, I'm showing this max minus minimum selenium carbon bond length. And you can see that it takes, about 30 femtoseconds. You've sort of stayed within the ring staying closed configuration. And then after 30 femtoseconds, you get this driving force that drives the system to longer bond lengths, which breaks the ring. And up by 50, 70, 80 femtoseconds, you've pretty much broken all of the rings throughout the trajectories. And this is, of course, at room temperature, 298 Kelvin, and we ran 200 trajectories. And what we found is, so this is, anybody who looks at this might think, well, okay, so you've shown that you can break the ring, but really the electronic structure for ring breaking is quite complex. And it is, and it requires typically, in order, if you want to form a radical or something like that, it requires electronic structure methods that include some static correlation, which TDFT does not, of course, right? So, and we're still trying to, and my group's actually looking at some of these calculations now, and we have some ideas on ways in which we can improve this. But it really stems from this predicting the dynamics past the Coulson-Fisher point. So we all know that if you look at a dissociative potential where you have a difference between the restricted and the unrestricted solution, that the point at which these intersect is called the Coulson-Fisher point. And the Coulson-Fisher point means that there's a bond length at which you can get a lower energy solution past it by allowing the electronic structure to unrestrict. And you allow the electronic structure to unrestrict at the cost of introducing spin contamination. So you can get a spin contaminated state that's a lower energy solution by allowing it to unrestrict. In the excited state, though, the excited state potential, and really this sort of unrestricted solution past the Coulson-Fisher point is generally a better way to approximate the electronic structure because you have a lower energy solution variationally. But in the excited state, these potentials look really strange past the Coulson-Fisher point. So for instance, if you were to leave the calculation restricted but break the selenium carbon bond, what you find is that past the Coulson-Fisher point, where you're still in the restricted formalism, you get smooth curves that at least qualitatively look correct. They connect correctly. They seem to dissociate to at least a limit. However, if you look at the unrestricted solution, which in the ground state you would believe to generally be better by the variational theorem, the potential energy surfaces go all ski-wampus, right? And you basically get this divergence of the surface past the Coulson-Fisher point where you get these kinks in the potentials. And people like Dip have have a great sort of analysis on some of these, but generally it's it's still an area that needs some work into understanding what the proper sort of representation is beyond the Coulson-Fisher point. And if you were to look at if you were to look at the simulations of the SQC simulations, you see that so here I'm showing the percentage of trajectories that have crossed the Coulson-Fisher point. By 10, 20 femtoseconds, you're still in the restricted regime. But by 30 femtoseconds, you've had about 20% of the trajectories which have crossed the Coulson-Fisher point with an average S squared of 0.1. But by the time you get to 70, 80 femtoseconds of simulation time, you have, 0.7 as the average S squared, and you have about 90% of the trajectories that have crossed the Coulson-Fisher point. So these are still open questions that we're investigating. Yeah. Okay. So, I've talked to you some about how we can predict dynamics through these near touching points or through these with these non-radiative transitions. When we were developing this, we came across some cases that were a bit unusual, and so we wrote a paper about it. And what we found is that when you have these near touching points or you have these points of non-radiative relaxation, it almost always signals, well, we didn't find this, but this is in the literature, it almost always signals that these near touching points have a nearby conical intersection. So here I'm showing the same potential with a conical intersection. These states cross. You have a minimum energy crossing point, and it's believed that these near touching points actually form seams that surround a conical intersection, these seams of near touching points. Well, if you look at our same sort of toy model of exciting a particle onto S1, if you have a minimum energy crossing point here, the particle will just pass right through that conical intersection. But these conical intersections can have different topologies. You can have what's called a peaked intersection, which I'm showing here, where the particle passes right through, or you can have what's called a sloped intersection. And a sloped intersection looks a little bit different, where you have the seam of near touching points, but now the crossing is sloped. And one thing that we found is when you have these sloped intersections, that if you were to excite a particle and the particle was headed down, that it can get trapped. The particle can actually get trapped near these seams of near touching points in what QChem predicts are minimum energy configurations. Now, there are these sort of artificial minima that occur just as a result of the distortion of the topology near a minimum energy crossing point. And QChem predicts them to be stable minimum energy configurations. The sort of indicator that these are not stable configurations are if you were to do a second derivative or harmonic frequency analysis. You would find that while QChem predicts this as a local minimum, you'll find that with a harmonic frequency analysis that you get harmonic frequencies that are very high usually. I mean, you'll get a harmonic frequency for a vibrational degree of freedom of this that's 6,000. We've seen them up to 20,000 wave numbers, which QChem predicts is correct. It's sort of really strange behavior. And we found a couple of cases that we presented in the paper. We call these fantastical excited state minimum energy configurations. And we found a couple of these. One is a really simple structure of phosphine. So here I'm showing phosphine. The minimum energy configuration of phosphine is a C3V symmetry. It's an S0. A1, the first excited state, S1, if you were to run a geometry optimization on the first excited state of phosphine, what you get is you get a planar structure that has a T-shaped, so it's C2V symmetry, T-shaped planar structure. Well, the next excited state is a degenerate pair of E states, S2. And if you were to run a geometry optimization on one of these states, you find that one of them optimizes to a minimum energy structure that looks like this, where it sort of is pyramidal, but it's not, you don't have an equidistant pH bond. It's sort of an elongated pyramidal structure. And if you were to run a frequency calculation at this S2 minimum, you find 5 modes that make perfect sense. You have a wagging motion of the hydrogens wagging out of the plane. You have this rocking motion here at 572 wave numbers. You have an in-plane bend at 1008 wave numbers. And you have some stretches. You have a symmetric stretch of the pH, and you have an antisymmetric stretch of the pH, all at about 2500 wave numbers. But there's one mode missing, and the one mode missing from this is a mode that basically combines these two configurations. It's a mode that stretches along this elongated pH bond and does a wagging motion of the two flanking hydrogens here, which basically connect to this T-shaped structure. So there's a vibrational mode that goes from this T-shaped structure to this S2 minimum. And the predicted harmonic frequency of this motion is 6,884 wave numbers. Well, if you take this vibrational degree of freedom and you do a potential energy surface scan along it, so you're just moving along this vibrational degree of freedom, what you find is that at 0, where 0 is the S2 minimum here, that you have a near touching point with the S1 state. You actually have one of these near touching points where you could have non-radiative relaxation. And if you, just by finite difference, if you move along this scan and you calculate the second derivative of the energy, we use finite difference in this case, but if you calculate the second derivative of this, what you find is that the second derivative all looks like it sort of is around 1000, would correspond to a harmonic frequency of around 1277 wave numbers. And then at the point where you have this near touching, you get this spike in the second derivative. And the spike peaks, at least with finite difference, at 8552 wave numbers. Now, if you were to also calculate just the derivative coupling that I've been talking about before as a function of this normal mode coordinate, what you find is that it perfectly coincides. It perfectly aligns with the second derivative, meaning that at the point where you have the maximum second derivative, you also have a maximum derivative coupling. We were then curious about, okay, let's say one of these minimum energy, these fantastical minimum energy configurations were stable. What's the time scale that state would be stable? What are the kinetics of a state like that? And in order to investigate the kinetics, we treated it just as a simple two-state system, two-level system, with a linear potential energies that have slopes G1 and G2, and they're linear in terms of Q. Now, if you were to look at a simple model Hamiltonian of this linear two-state structure and have your diagonal elements as a function of Q just be those potential surfaces, and you were to have a constant coupling, constant diabatic coupling between states 1 and 2, then you would get a 2x2 Hamiltonian of this form. If you diagonalize that 2x2 Hamiltonian, you get the energies of the states in the adiabatic representation. They look like this. Well, if you were then to take those adiabatic states, the eigenvalues of those adiabatic states, and calculate the second derivative of that, so you calculate the second derivative of the energy of the upper state, in this case, with respect to Q, and evaluate it at Q equals 0, you get this expression. So this expression here says you have a difference of gradients squared in the numerator, and then in the denominator you have a 4 times the coupling strength. Well, as the coupling between those states goes to 0, then this term becomes undefined, right? This term actually blows up, and that's the cause, mathematically, of this peak in the second derivative. For the kinetics, we then propagated classical trajectories. We did this analytically because they're just linear surfaces. And we used a Landau-Zener transition probability in order to calculate the lifetime of these states, of this state. And for the phosphine case, what we found is that the lifetime, so if you propagate these dynamics and then calculate the Landau-Zener probability as you go through the crossing point, what we find is that the lifetime of that state after it's been fit to an exponential is like only 4 femtoseconds, right? So in our simple case, it basically would fall down to the lower state almost, I mean, it would only have a lifetime of 3.76 femtoseconds. This occurs in bigger systems, like here I'm showing ruthenium, that ruthenium chromophore that I was showing in the dye-sensitized solar cells slide. We found it also in this ruthenium bipyridine complex, where if you look at the potential energy surfaces on state S3 in this case, state S3, you have this near touching point with S2, and you form this fantastical minimum energy structure. The mega mode or the fantastical, the mode that sort of has the ultra high vibrational frequency involves stretching of the pyridines. You have an in and out of phase stretching of two of the flanking pyridine molecules. If you do the same second derivative analysis, you find it's a bit more interesting now because you have multiple of these near touching points. And if you do the second derivative analysis, you can see that each of these near touching points coincide directly with derivative coupling peaks. So these things are related. There's definitely a derivative coupling that's associated with these spikes, these peaks in the second derivative. A Landau-Zener transition probability analysis of this gives similar results. So here, if you linearize around the S2, S3 near touching point, or the fantastical minimum energy structure, and run these same trajectories on these linear potential energy surfaces, we find that the lifetimes is 5.6 femtoseconds. So these things just fall right down to the lower energy states. Okay, so I would like to thank you guys for listening to me today and for thank the award committee for giving me the Nick Besley Award. I'd like to thank my postdoc advisors, Martin, Steve, and Bill Miller. For the non-adiabatic dynamics work, we were funded through the NSF, and we were funded through the US Department of Energy. Then the SQC non-adiabatic dynamics code is available in the release version of QChem. For the computations, we used NERSC. For the fantastical excited state stuff, I did this with one of Martin's graduate students, Juan. He's now at Sandia. My undergraduate and my graduate research was done with Ryan Steele at the University of Utah. So I'd like to thank you guys for listening to me, and I'm happy to take any questions.
All right. Thank you so much. That was a wonderful talk. Anyone who has questions can go ahead and either post them in the Q&A or the chat down at the bottom. And yes, you should all be able to post to the chat now. So. All right. Well, if nobody has questions, can you go back to the slide about I have strong correlation, the static correlation one.
Oh, right.
I know this was like a really brief thing that you touched on, but what would happen if you tried using spin flip TDDFT with that? Is that
Yeah.
is
Yeah.
that
So
a possible solution?
yeah. So I'm not sure past the. So maybe John has tried this. I haven't tried this past the Coulson-Fisher point, but spin flip definitely helps with the formation of radicals. So I think that it would help if you use spin flip. The thing that I'm not really sure about is how you handle the spin contamination. So when you do spin flip, you usually introduce a pretty substantial amount of spin contamination. And spin contamination in the non-adiabatic dynamics sort of trajectory is something that is still not really sure how to proceed with that, right? Because you would typically want to be propagating on pure spin states. So if you were doing spin flip like excess, spin flip excess,
Mhm.
where you can get pure spin states from that, then that would make a lot of sense. If you can pay the sort of energetic cost that you get at not having very accurate potential energy surfaces, that would work quite well. For spin flip TDDFT, to my understanding, there's no spin flip complete version of TDDFT, that it's actually just not possible. Now, QChem has this sort of I forget what it's called, but it has this sort of ad hoc spin flip complete setup. I'm not sure how that would perform in cases like this, but yeah.
Okay, cool. Thank you. I'm I'm more familiar with the Exis side than the
Right.
TDDFT side, and so uh, yeah, that totally makes sense though. Thank you.
Yeah.
Um, does anyone else have questions? I know we're coming up on noon Pacific time here. Oh, one person has a question. Same slide relatedly, are there any other methodologies you are considering beyond the Coulson-Fisher point?
Yeah, great question. So we've in my group now, we actually have a method that we're looking at where you take, and we're almost ready to publish this, but you take this expression here, and in this expression, you have to solve the couple perturbed equations in order to get the relaxed density matrices. Well, those couple perturbed equations are just the orbital relaxation that goes into the density matrices. Well, that orbital relaxation term from that expression that we put in the SQC paper for the solution of the couple perturbed equations is basically the Lagrangian of that is the orbital rotation gradient. So you can optimize the CIS state or the TDDFT state in the presence of, or optimize along that orbital rotation gradient. That has to give lower energies overall for the CIS excitation. It seems to completely break once you pass the Coulson-Fisher point, though. So you can optimize the orbitals all the way up to the Coulson-Fisher point. And then once you pass the Coulson-Fisher point, the calculations just don't converge anymore. There's no orbital optimization that takes you past the Coulson-Fisher point. So that's something that we're working on now. We think we have a working sort of approach to optimize orbitals for the excited state for like TDDFT, but yeah, more to come with that. Sure.
Excellent. Thank you. Um, does anyone else have any questions? All right. It's just about noon. So
Great.
if nobody else has anything, thank you very much for an excellent talk. It's been really exciting to hear about the work you've been doing, and congratulations again on receiving the award.
Yeah, thank you
Um,
so much.
Thanks. And then for those of y'all in the audience, if you wake up in the middle of the night tonight realizing that there's a question that you're burning to ask and have forgotten, then we will be posting a thread on the QChem forum where you will be able to ask any questions after the fact. And also, if you would like to review this talk, we will be posting it on our YouTube channel before the end of next week. So thank you again, and congratulations again. And we appreciate your time. Thank you.
Thanks.
Have an excellent Thursday, everyone. Bye.